Okay, geometry students, welcome to lesson 2 of unit 1. Our focus today is going to be on angle measures and also an introduction to the idea of proof. So we're going to be classifying angles and identifying and using postulates about points, lines, and planes. And so what I'm going to do is just try to talk you through these 5 postulates and just explain them. Some are pretty self-explanatory, others warrant a little bit of explanation. And so again, all of these will be given to you. They'll be on your theorem sheet. It's a theorem postulate sheet, and so there's no need to memorize these. You just need to understand them. Okay, so if we have 2 points floating around in space, if you were to join those with a line, they are joined with exactly 1 line. So 2 points, through any 2 points, there's exactly 1 line. Through any 3 non-collinear points, there is exactly 1 plane. And this was actually something that we alluded to in the previous lesson, in one of the examples in the previous lesson. And so let me jump back to that for just a moment and try to remind you. And so this was the example in which we had points F, G, and H, and we were able to establish that there is a plane that passes through those 3 points, and that is affirmed by this postulate that says through any 3 non-collinear points there is exactly 1 plane. Remember, non-collinear means that the 3 points must not be on the same line. If, of course, we had 3 points that were on the same line, this is not enough to define a plane because it only has 1 direction or 1 dimension, and of course for a plane we need 2. Okay, a line contains at least 2 points. No need really to explain that. It's somewhat self-explanatory and covered by postulate 2.1. Similarly, a plane contains at least 3 non-collinear points, as I explained above. The points must be non-collinear, otherwise we do not have enough information to create the plane. The important thing to understand, though, is when it says at least 3, there could be more than 3. In fact, of course, a plane contains an infinite number of lines and therefore contains an infinite number of points. Okay, and if we move to the final of the postulates for today, if 2 points lie in a plane, then the entire line containing those points lies in that plane. Of course, that's because planes are 2-dimensional, lines are 1-dimensional, and so if the 2 points are contained within the plane, then all points that lie in that dimensional direction must also be contained within that plane. Okay, and so now we're going to try to apply some of these in what we learned last lesson. For each of these statements, what we're going to try to do is determine if they are always true, sometimes true, or never true, impossible. Under no circumstances could it be true. And so we're going to try to explain the reasoning, and I'll do that with some diagrams. So if 2 lines are coplanar, that means they share the same plane, they will intersect. That is going to be a sometimes true statement. The reason is, so I'm going to draw a representation here of a plane. That plane is going to contain 2 lines, and the 2 lines in this particular case show a very clear point of intersection. But we do have another possibility, and that is, of course, within the plane, we have 2 lines that are coplanar, but those 2 lines are, in fact, parallel to each other, and that would be the instance in which they would nonetheless be coplanar, but they would not intersect. Okay, to the next question. 3 points are non-collinear. That means if you have 3 points, they do not share the same line. This, of course, is also sometimes true. You may have the following instance. You may have a line which contains the 3 points. And so this is an instance in which you can see that the statement is not true. We have 3 points, but they are collinear. And of course, the other example which supports the statement is if 2 of the points were on the line and the 3rd were not. This would be an instance in which the statement is true. This is the instance in which it's false, and therefore we're going to say sometimes true for our conclusion. Okay, if 2 lines intersect, then they are coplanar. And so what I'm going to do is use the diagram from above this one over here, what we can see is, or hopefully what you can see is, that this is going to be an always true statement. If the two lines intersect, what it guarantees is that there are only two directions or two dimensions, and of course anytime we only have two directions or dimensions, then we have a plane, and so those two lines will be contained within one plane. The counterexample, of course, is if the two lines are not parallel. So in this particular case, we're not considering the parallel option because we've already been told that the lines intersect, and so we can guarantee that they are coplanar. If the lines were not intersecting, we do have an instance where they're coplanar, and we have an instance where they're non-coplanar, but I'm going to show you that in a future lesson. It's something we refer to as skew lines. Okay, and then we come to our part D of example 1. 4 points are non-coplanar, very similar in character to question B. So if we have 4 points, that means they do not lie on the same plane. Of course, we know from one of the postulates above, postulate 2.4, planes can in fact contain an infinite number of points, at least 3, and so we could very easily have the following, where the 4 points that we are referring to are all contained within, let's call it plane X, but we might have a different example where we have 3 of the points defining a plane. So we'll have plane Y, we have 3 points that are non-collinear, so they've got 2 different dimensions or directions. So we've got 2 different dimensions or directions, and then we have our 4th point, which lies above or below the plane, and this is an instance in which 4 points might be non-coplanar. This is an instance in which 4 points are coplanar, and so this statement would be sometimes true. Okay, moving on. So this little bit of explanation here, really just some more definitions and language of geometry that you really need to learn to speak as quickly as you can. So as mentioned in the first lesson, a postulate, also known as an axiom, is something we accept without a proof. We use undefined terms, definitions, properties, and postulates to make a conjecture, and we prove that conjecture, which results in a theorem. We then use those theorems in turn to prove other theorems. Okay, the process of proof, and again, we get in a couple of lessons time, we're going to start proof. The process of proof really involves going through a multi-step stage, depends what you've been asked to prove. Each statement you make needs to be supported by a justification, and then ultimately we conclude whether or not we were able to prove the conjecture. Okay, so I'm going to move to the first of our theorems. We are in fact not going to prove this. It is, at least to me, more like a postulate because it's somewhat self-evident, and so we are not going to formally prove all of our theorems. Some we'll just do by explanation, some we'll treat as postulates, and some we'll prove formally. Okay, and so if M is the midpoint of AB, so M is the point that lies halfway between A and B, then we have the theorem that says, therefore, segment AM must be congruent to segment MB, and in this case that means they are going to be equal in length. Okay, we're going to turn our attention now to angles, and I'm going to talk you through some stuff relatively quickly so I have time for the examples. And so in the first lesson we made mention and defined a line and a segment, and what we're going to do is define the third possibility, which is a ray. Of course, lines continue forever in both directions. Segments have got defined starting and ending points, or 2 ending points, and then when we're dealing with a ray, we have a defined starting point that continues forever in one direction, and so rays are typically named, as with lines and segments, with 2 letters, but the difference being that in this particular case, ray AB has A as the starting point passing through B. You can also name this as BA, but then of course we must turn the arrow around, and that's the same thing. Okay, so ray is a part of a line, and as mentioned, one endpoint, and it extends indefinitely or infinitely in one direction. Okay, opposite rays, these are rays that share a common endpoint, they are collinear and they extend in opposite directions. And so effectively what this means is, what we really have is a line essentially with one ray going in that direction, the other ray which shares this point going in that direction, and since they effectively form a line, but those are what is known as opposite rays. Excuse me. And finally, what we have is the definition for an angle. And essentially, you can see the picture over here. An angle is formed where you have two rays that have got the same endpoint, but they are non-collinear, and so they're not on the same line. They're not going in opposite directions. Right now we have ray FE and we have ray FG, and they join together with common endpoint F. F is known as the vertex. So F is the vertex of our angle, and this angle can be named as EFG. So we could go from E to F to G. We can go from G to F to E as long as F is the vertex. We could also call this angle 1, and finally we could also call this angle F. The exception to calling it angle F is, of course, if we had another angle here, let's say, and this was FR, then to call it angle F would cause confusion about which of these angles we were talking about, and so be careful about calling things angle F, particularly if there are multiple angles that share the same vertex. Okay, hopefully this is all prior knowledge for you. So right angles are 90 degrees, acute angles are less than 90, obtuse between, so bigger than 90 but smaller than 180, and a straight angle 180 degrees. Two more definitions, and then we're going to wrap up the last two examples. So congruent angles are angles that are equal to each other, just like congruent segments from the last lesson. And lastly, we have the idea of a bisector. When you see bisect, cut into two equal pieces. So cuts in half is really what that means, and that is going to apply both to segments and to angles. And then the last bit over here is actually called the angle addition postulate. And it's very similar to the segment addition postulate. It effectively says the sum of the parts of an angle give you the whole angle. And that's fairly self-evident. We'll do a couple of examples that highlight that. Okay, so I'm going to pause again and fill some info in just so I don't run out of time. Okay, so all I've done in this example is I've written in 5x plus 9 over here because we were given that angle ABD was 5x plus 9, and I've also filled in that angle EBC is 2x because that was also given information. Basically, we've been asked to find angle ABD, which is to find this angle here. To do that, we're going to need to know the value of x. And so there's one other piece of information I have not yet used or put onto the diagram. We're given line AB. We have BE bisecting angle DBC. So angle DBC is bisected, which means it's cut in half by ray BE. And that means that this angle here must be equal to this angle here, which allows me to write 2x in for the measure of angle DBE. And I can now use the fact that since this is a line, it's a straight angle, and the measure of angle ABC is going to be 180 degrees, and that allows me to find my equation 5x plus 9 plus 2x plus 2x equals 180, and now I'm going to solve for x and sub back. Okay, so what you can see is I've solved this equation to get x equals 19. I've substituted back into the measure of angle ABD 5 times the value I found plus 9 to give 104. For the final example, again, I've transferred the information onto the diagram. ABD was 39, ABD, CBD was 3x minus 6, and the entire angle was 5x plus 5. In this case, to get our equation, we use the angle addition postulate, which says the sum of the pieces of an angle, which in this case are 39 plus 3x minus 6, must give you the total. Sum of the parts gives you the whole. And now I'm going to solve and substitute back. Okay, so very quickly I've solved for x equals 14. I've subbed that into the expression, and I have the answer of 36. Very important in this case, never assume because it looks like 90 that it is that would have given you the wrong answer.